Hello friends, this is Jim with Science Talk. Have an interesting story, and by analyzing what's going on with this situation I'm about to share with you, we might be able to get a hint of what we might come to expect now. The asteroid that smacked into off the Yucatan Peninsula and ended most dinosaurs' time on Earth. Birds, of course, persisted, and they are dinosaurs. That impact warmed Earth's climate for 100,000 years. Interesting. Carbon dioxide released into the atmosphere after the impact of the Chicxulub asteroid warmed the Earth's climate for 100,000 years, a new study has revealed. The study, based on analysis of fossil records, suggested that the Earth's overall temperature increased by 5 degrees Celsius, about 9 degrees Fahrenheit, over that time. The results raise concerns about how long it will take for the planet to recover from the effects of human-caused greenhouse gas emissions, said Kenneth MacLeod, a professor of geological science at the University of Missouri and lead author of the work that's been published in the journal Science. Scientists have long theorized that after that big rock that came tumbling down had a diameter of 6 to 9 miles, smashed into the Yucatan Peninsula near today's town of Chicxulub in Mexico. The temperature of the planet first rose sharply for minutes or hours. After that, it plunged down for months to decades. Now, decades, because of all blocking out the sun, that will be sufficient to basically halt photosynthesis. And when that happens, you have a massive die-off of the organisms and so on and so forth. So you would not need a long time period, geologically speaking, to kill off a great majority of species. A few decades would do the trick. Okay? So right, you have the dust, the soot, stops photosynthesis. Life without photosynthesis, no plant producing food, nothing for the herbivores to graze upon. They die. The carnivores can't eat. The only ones that might persist for a little bit are the scavengers, and then after a while they're going to run out. So we thought, this is Professor MacLeod saying. Now, before I continue with his statement, eventually, though, the CO2 that was released did start holding, because once the soot started settling down, we had the CO2 in the atmosphere. Now the sunlight is coming through. Now the heat can start being trapped. Now up goes temperatures. So, Professor MacLeod, we thought we could resolve this question by looking at fossilized bits of fish teeth, scales, and bones from the El Kef section in Tunisia. Now, El Kef's section in Tunisia is a paleontological site in northwestern Tunisia, known for having one of the world's best preserved fossil records from the period before and after the Chicxulub impact. The researchers looked at concentrations of different oxygen isotopes in the fossils. I did a video some time ago called isotopic fractionation, where I discussed O18 to O16 ratios and how we use that in the ice cores, in the shells of forams, the diatoms, other phytoplankton and single-cell organisms, and how we use that information to help reconstruct past climates, past temperatures, and so forth, in conjunction with measuring CO2 levels. That's a case of where we have different methods of measurement to back up the data. There's also C13 to C12 ratios. There's N15 to N14 ratios that are done. We have multiple techniques at our disposal to back up our data. When we try to go back hundreds of millions of years, we don't have that luxury. and as a result we have huge errors, and so we can't really state with any confidence or accuracy what CO2 levels might have been. We have a hint of temperatures because we can look at the species grouping. What kind of species are there? Warm weather, cold weather species, that kind of stuff. Anyway, so they looked at this, the ratio of the different oxygen isotopes, O18, O16 primarily, and these isotopes differ, of course, in the number of neutrons that they have. Okay? If you change the number of protons, you have a different element. So O16, oxygen always has 8 protons. So 16 minus 8 is 8. So you're going to have 8 neutrons. O18, well, 18 minus 8 is 10. So there's going to be 10 neutrons. So there's also an O17, but that's a little more rare occurring. So one of the differences, as temperature increases, the amount of the light oxygen isotope O16 in the mineral increases relatively. Now, I have to admit, when I read that statement, I was like, huh? Because usually what we have when we've done our ice cores, and we look at the forams, to build up the ice sheets onto the land, okay, you're going to evaporate, you're going to take the water from the oceans, send it into the atmosphere, precipitates as snow, comes down and compacts as ice. Well, O18 is heavier, so the O16 is more likely to make it into as water vapor. So when we look at the ice cores, what we see is we always measure, well, we measure as the O18 to O16 what we call fractionation. So we see that ratio decrease in the ice cores during the ice age, but the O18 that's left behind in the waters, well, the organisms who make the shells, test, right, we call them, silica, carbonates, what have you, we see an increase in the O18 in the shells of these organisms during ice ages. Here he's saying the opposite, and then here's his next statement from the report. We are measuring the ratio of oxygen 16 to oxygen 18. He's doing a reciprocal. If he had stated the O18 to O16, then if he had done it that way, then as the temperature increases, the amount of the light oxygen isotope O16 should decrease relatively. Okay, so he was looking at the ratio in a different way. But generally speaking, this is kind of this is one of the things we look for. Ice ages, heavier O18s left in the ocean. Organisms incorporate more because it's more available relative to O16 into the shells. So during ice ages, we see that ratio in the organisms go up, but in the ice cores go down. The reverse happens in interglacial. The O18 goes up in the ice cores, goes down in the organisms. But the point of it is that every 1 part per thousand that the ratio changes correlates to about a 4.5 to 5 degrees Celsius change in temperature. That is not much. The researchers analyzed 40 samples taken from the site in Tunisia, 10 samples from the 50,000 year period before the impact, 20 samples from the 100,000 years immediately after the impact, and an additional 10 samples from the following 200,000 years. We found that there was a really big difference in oxygen isotopes between these 3 sets of samples, unambiguous. So now he wants to check this preliminary data against fossil samples from other parts of the world, and wants to check for similar patterns. So the study, McLeod said, not only sheds more light on what happened to the Earth's system after this kaboom, but it also raises questions about the consequences of what humans are currently doing. If I were to draw a line under the lessons of this study to the modern era, it would be to contemplate the idea that what we are doing in our lifetimes will affect the Earth for the next 100,000 years, which is pretty daunting. So, very interesting study. And again, using the isotopic fractionation can reveal important information. We can construct the data. Using the data, we can construct the climate. It makes sense that you have the initial soot and ash blocking the sun. It remains in the atmosphere for decades to come. No photosynthesis, ecosystems, organisms, crash, die, and so on. Then the soot eventually settles down, but the CO2 is left in the atmosphere, which then starts trapping the heat, and temperatures go up significantly. And we can measure this by looking at the isotopic ratios. There are other isotopic ratios that can be examined, but believe it or not, there are whole semester courses geared solely to isotopic analysis. So it is a very valued tool that paleoclimatologists utilize in trying to reconstruct past climates, in addition to looking at the organisms and so on and so forth. So, thank you for your time. We'll talk soon. Hey folks, just a reminder to please subscribe and click the bell so you know when I drop a video. Please share my videos. Please tell others of my channel and of the work that I do. I also hope that you will consider becoming a patron at patreon.com/Science Talk with Jim Massa, where from time to time I upload videos there exclusively for my patron subscribers. Details in the description box below. Thanks.